Good morning. So we're going to try section 5.1 again, the natural logarithmic function differentiation. So first off, I don't think I told you the other day, the natural log function is defined ln of x equals 1 to x of 1 over t dt. So if we have this situation, to go backwards, if we have this situation, we would know its answer would be ln of x. But the domain is 0 to infinity, as you can see from this graph. The range is negative infinity to infinity. It's continuous, it's increasing, and it's 1 to 1. 1 to 1 just means it passes the horizontal line test, so it has an inverse. And it's concave downward. So this is just a little review of natural log. But what I really wanted to do was these logarithmic properties with you, which is the page I asked you all to read. But I'm not sure, I know some of you did, but I don't think all of us read it. So the first property, ln of 1 is 0. And the reason why, remember natural log is a base of e, and if you do the swoop, write it as an exponential, e to the 0 is 1. So there's that property. Number 2, the ln of a product can be rewritten as the ln of a plus the ln of b. So we can rewrite a product as a sum. We got that same symbol there. Likewise, the ln of a quotient can be ln of a minus ln of b. So if you have a quotient, it's subtraction. And last, ln of a to the b. Is that how they did it? A to the n. We could take the power and move it in front of the logarithm. So these are all properties we used a lot in pre-calculus. We're just reviewing them. You should look at example 1 on how to expand logarithms. Remember expanding and condensing using these 4 rules. You should look at example 1. The next thing they're going to talk about is e, which is the base of the natural log function. E is that Euler's number. Remember, it's German. It's pronounced Euler's number. And it's irrational, like pi, 2.718, and so on. Then you should look at example 2 and just make sure you can do those on your calculator. But we are wanting to get to page 322, which are the 2 properties that we wrote down in class the other day. The derivative of the ln of x with respect to x is 1 over x, as long as x is greater than 0. And its cousin, which is more handy, is the derivative of ln of u with respect to x is 1 over u times u prime, as long as u is greater than 0. So these are the 2 properties. There were 3, but we're not going to get to it yet. So let's see how to use it. Example 3, A part. What is the derivative of the ln of 2x with respect to x? Well, that fits the second property, the ln of u. The only time you're going to get to use this first property is when it is just x. And that doesn't happen very often. Normally there's something here. So we've got 2x. That means u is 2x. So u prime is 2. So our answer is just 1 over u times u prime. And the 2's cancel, so it's just 1 over x. I think we did that one in class. B part. What if we have, the derivative of the natural log x squared plus 1 with respect to x? That is all u. U is x squared plus 1. So du or u prime, I'm going to go with u prime today, is 2x. So we follow the rule. It's 1 over u times u prime. Nothing cancels, so it's 2x over x squared plus 1. And remember, I love math doesn't work upside down. That does not work. C part. I think we did this one in class too. What's the derivative of x ln of x? You have to get your mind thinking about derivative rules again and say this is the derivative of what type of problem, and that's a product. So that's that a b prime plus b prime a, which is first derivative of second, derivative ln of x. Oh, look, you finally get to use this first rule. Is 1 over x plus second. I didn't write that property right. Second times derivative of first. It's not, let me fix this. That ABA rule. First derivative of second plus second derivative of first. There you go. All right, this simplifies to 1 plus ln of x. All right, D part. I think these are fun because I like logarithms. So ln of x all to the third power. All right, so what we want to do is there a way that I could use a property? Actually, this isn't one of our properties. This is chain rule. So this is u would be ln of x. U prime would be 1 over x. This is the way this works. This is like we have u to the third, and we're trying to take the derivative of it. So chain rule says it's 3u squared times u prime. I've got to do the derivative of this, the inside part, but then I've got to do the derivative of, no, not the inside part. I'm going to do the derivative of something to a power using power rule, 3u squared. But then I've got to take a derivative of the inside part. So that's the chain rule part. So you don't have to think of it with u's. You could do it this way. You could say, okay, that's something to a power. So when I do the derivative of something to a power, it's 3 times that something to 1 less power times the derivative of the inside part. So we could do it that way. So that is, that's 3 ln of x squared over x, or we could write it as 3 ln squared of x over x. So it's important that we remember these two things are equivalent. Just like you can do it with the trig function. It also works with logarithms. Alrighty, example 4. What if we have a function f of x equals the natural log of the square root of x plus 1, and we want to take its derivative? Well, I would say that's also like a chain rule problem. Let's rewrite it friendlier. X plus 1 to the 1/2 power. That's basically the same as that. I mean, kind of. Not really. Not really. It is different. So what would we do here? We can bring the power to the front, actually. This is property 4 that we talked about. This is that ln a to the n can be written as n ln a. So we can bring that property to the front and then differentiate. So we want to use log properties to simplify as much as possible before we're ready to try to take the derivative. So when we do the derivative, that 1/2 is just a constant. And then this is the ln of u. This is that second rule we wrote down today. So it's 1 over u times u prime. So that is numerator, numerator, numerator over denominator times denominators. All right, we'll do one more. One or two more. Example 5. What if you have f of x equals natural log of x times x squared plus 1 squared over the square root of 2x squared minus 1. Wow, that is a lot. But it's the natural log of all of that stuff. That means we're going to be able to do a lot of expanding to make this nicer, rather than jumping in and calling all that u and then having a big difficult quotient rule problem to do. Let's use log properties to expand. So that's the same thing as the ln of, this is a big product at the top, so break it apart, ln of x plus ln of x squared plus 1 squared. So that was the log of this product, this times this. And now we've got a quotient, so minus the ln of 2x, whoops, let's not skip steps, of the square root of 2x squared minus 1. So far we've used log properties. Log of a product can be written as a sum. Log of a quotient can be written as a difference. And now I can't do anything to this first term. The second term, this exponent can come down to the front. And this third term, I could have written it as 2x squared minus 1 to the half. So that exponent can come down to the front. So you might say, well, that doesn't look any nicer at all. But let's now do it one little step at a time. So we've rewritten it as much as we can. So now let's do the derivative. The derivative of this first term is 1 over x. The second term, so plus 2, it's a constant, times 1 over u times u prime, minus 1/2 constant, times 1 over u times u prime. Let's see what simplifying we can do. Make everybody fractions here. So it's 1 over x plus numerator, 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 4x over x squared plus 1 minus 4x over 2 times x squared minus 1, or 4x squared minus 2. We could get a common denominator, but I think they are not making us do that. Let's see. So I just looked back just to double check my answer with the book, and I noticed they didn't agree. But it's because I didn't copy the problem down right in the problem in the book. In case you look at it and try to rework it, the original problem, this was a third power. It was 2x to the third. So that's why. I'm not going to do example 6 with you. We're going to let you practice these. So you will be ready to tackle your homework now. All right, so go ahead and look at facts and start working on these problems.